So we've already talked about arithmetic and geometric sequences. Now I'm going to talk about arithmetic and geometric series. A series is the sum of the terms of a sequence. A series can be finite. That means it has a certain number of terms, or it can also be infinite, and that means that it goes on forever, essentially. This is what a series looks like. You have your first term, addition sign, second term, addition sign, third term, addition sign, and it goes on. That is a series. The sum of a series is actually when we add all these together. So the sum is when we add them. The notation for arithmetic and geometric series is almost the same as it is for sequences. The only thing is we're adding on this, and that means the sum of the series to the nth term. So the arithmetic series formula is S sub n, so the sum of the nth term is a sub 1 plus a sub 2 plus ... all the way to a sub n. And then there's actually a formula for it. There's a funny story about that. Well, you might not think it's that funny. There was a 10-year-old, and the teacher gave the students in this class the numbers from 1 to 100 to add up. And one of the students, in a minute, said, "Here you go, here's the sum." And he's responsible for the formula that we are going to use today. His name was Euler. It's spelled E-U-L-E-R. He's one of the most talented mathematicians that we've ever had. All right. So, the sum of an arithmetic series to the nth term is the number of terms divided by 2 times the first term plus the nth term. That's the formula that Euler came up with. The sum for a geometric series, the formula for that, is the first term times 1 minus r to the n, however big you're trying to, however many terms you're trying to add up, divided by 1 over r. All right, here's an example. I want to find the sum of the 18th term, the first 18 terms. That's what that tells me. For the sequence 13 plus 2 plus negative 9 plus negative 20 plus ... all the way to 18. Well, I need to figure out what kind of sequence this is first. So if I look, 13, to get from 13 to 2, I have to go backwards negative 11. To get from 2 to negative 9, also the same thing. And then from negative 9 to negative 20 is also negative 11. So that means that this is an arithmetic sequence where the difference is negative 11. So I'm going to go ahead. I want the sum of the first 18 terms. So I'm looking for 18 over 2. My first term is 13 plus my last term, my 18th term. Wait a minute, I don't have my 18th term. That means I have to go find it. So I'm going to use the same formula to find the, not the sum. I'm going to use the same formula I used before to find the 18th term. So 13 plus 18 minus 1 times the difference, which is negative 11. Oops, this is 18, not n. And that's going to be 13, and then 17 times negative 11 is going to be negative 187. So the 18th term is going to be negative 174. So I can go ahead and plug that in now, and I get 9 times 13 minus 174, which is going to give me negative 1449. Okay, it's your turn. I want you to find the sum of the first 12 terms here. Turn this off and turn it back on when you're ready to check your answer. Okay, the first thing we need to do is determine what kind of sequence this is. If it's arithmetic, it's going to have a common difference. If it's geometric, it's going to have a common ratio. 95 minus 101 is negative 6, 89 minus 95 is negative 6, and 83 minus 89 is also negative 6. So this has a common difference of negative 6, and this is an arithmetic sequence. So we're going to use the sum for an arithmetic sequence. We want the 12th term divided, we want the sum of the first 12 terms. There are 12 terms. We divide that by 2. The first term is 101. We are missing the 12th term, so we need to find it. We're going to do that using the regular arithmetic sequence formula. That's going to be 101 plus 12 minus 1 times negative 6, which gives me 101 plus negative 66. That means my 12th term is 35. So I'm going to go ahead and put that up here in my formula. So I have 6 times 136. That means my sum of the first 12 terms is 816. All right, so geometric series. Let's find the sum of the first 7 terms. So for this one, the sum of the first 7 terms is the first term times 1 minus the ratio. Oh, I forgot to find the ratio. 42 divided by 14 is 3. And if I go ahead and check all the rest of them, all those ratios are 3 as well. So 3 is the ratio to the 7th power over 1 minus 3. Okay, so grab my calculator. That is 1 minus 3 to the 7th is going to be negative 2,186 over negative 2. 1 minus 3 is negative 2. And when I calculate that out, I get 15,302. That one's easier because I don't actually have to go in and find the 7th term. I just need the first term. You guessed it, you're going to try this one. Turn this off and turn it back on when you're ready to check your answer. Okay, let's check and find what the ratio is. This is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. And 16 divided by 8 is also 2. So my ratio is 2. So the sum of the first 8 terms is going to be my first term times 1 minus the ratio to the 8th power over 1 minus the ratio, which is 2. 1 minus 2 to the 8th divided by negative 1 gives me 255. All right, sometimes it's necessary to consider the sum of a geometric series as the number of terms gets very large or effectively goes to infinity. So what happens to our sum in this case? Well, there are 2 things that can happen. If our ratio is greater than 1 or less than negative 1, then the absolute value of the sum gets increasingly larger. And there's no infinite sum as we say, and we also say that the series diverges. But if our ratio is between -1 and 1, then each term gets smaller and smaller until it approaches 0. We say the series converges and has a sum. And the formula for this is, I have this sum of an infinite series is equal to the first term divided by 1 minus the ratio. And this only happens if our ratio is, the absolute value of our ratio is less than 1. So here's an example of how we might use this. We want to write this decimal as a rational number, and a rational number, if you've forgotten, is a fraction. And this decimal here with the sign over the top means that the 7 just keeps repeating. So if I'm going to first rewrite this as a sequence, or no, as a series, sorry. So the first term would be 7 over 10 plus 7 over 100 plus 7 over 1,000, and that would just keep going on forever because that's what that line over the top is saying. Okay, so now we can find the ratio. 7 over 100 divided by 7 over 10. If I want to calculate that, I'm going to reciprocate that bottom and multiply. My 7's will cancel out and the 10 will cancel out and leave me with 1 over 10. So 1 over 10 is my ratio. All right, so now to find the sum of my infinite series, I take my first term, which is 7 over 10, right? My first term is 7 over 10. I'm going to divide it by 1 minus my ratio. Remember, my ratio is 1 over 10. All right, and now I'm going to simplify that. 7 over 10, 1 minus 1 over 10, that means it's divided by 9 over 10. Now I have a fraction over a fraction. I'm going to reciprocate this and multiply. And I can cancel out the 10s and I'm left with 7 over 9. That's the sum of my infinite series, and that's also 0.7 repeating written as a rational number. You guessed it, here's one for you to try. I want you to write the 0.9 repeating and then check your answer when you're done. Alright, so let's first write this as a series. First term would be 9 over 10 plus 9 over 100 plus 9 over 1,000, and so on. And our ratio, remember we take our term and divide it by the previous term. And I'm going to reciprocate that because I have a fraction over a fraction. The 9's cancel out, and 10 over 100 equals 1 over 10. And that's my ratio. And you could check that next term too if you didn't believe me. So the sum of my infinite series is going to be my first term divided by 1 minus my ratio. And if I simplify that, I get 9 over 10 divided by 9 over 10. I don't even need to reciprocate that and multiply because I have the same thing up top and the same thing on bottom. Anything divided by itself is equal to 1. Alright, so let's say we just want to take an infinite sum for a series that's not a repeating decimal. So I have this series here, and if you look, each term gets smaller. If my terms are getting smaller, generally my ratio is less than 1. So if I want to find the ratio, 1/4 divided by 1/2, right, it's the term divided by the previous term. Now I need to reciprocate the bottom and multiply, and 2 over 4 is going to leave me with 1 over 2. So 1 over 2 is my ratio. So the sum of my infinite series is my first term divided by 1 minus my ratio, which is 1/2 divided by 1/2. Again, I have the same situation I had before. I have the same number on the top and the same number on the bottom. That's always 1. Let me warn you, though, that's not always going to be the case. Here's one for you to try where it's not going to be the case that the sum is 1. Go ahead and turn this back on and check your answer when you're done. All right, so let's check our ratio. 1 over 16 divided by 1 over 4. Reciprocate that bottom and multiply. It's going to give me 1 or 4 over 1. And when I cancel out, I'm left with 1 over 4. So my ratio in this case is 1/4. All right, so the sum of my infinite series is my first term divided by 1 minus my ratio. So that's going to give me 1/4 divided by 1 minus 1/4, which is 3/4. And then I'm going to reciprocate this bottom and multiply it by the top to get rid of that complex fraction. The 4's will cancel out, and I'm left with 1/3. And that is the sum. All right, I'll see you in class.